The use of 3.5-inch conduit is relatively uncommon, and most electricians typically upsize to 4-inch conduit for several reasons. Firstly, availability. As you mentioned, 3.5-inch conduit and fittings are not as readily available as 4-inch sizes. Supply houses may not stock a wide range of 3.5-inch fittings, making it difficult to obtain the necessary components for your project. Secondly, cost. In some cases, 3.5-inch conduit and fittings may be slightly more expensive than their 4-inch counterparts. While the price difference may not be significant for small projects, it can add up for larger installations. Thirdly, ease of installation. 4-inch conduit provides more room for pulling wires, making it easier to install and maintain electrical wiring systems. The larger diameter allows for easier cable management and reduces the risk of wire damage during installation or maintenance. Fourthly, code compliance. In some jurisdictions, electrical codes may require the use of 4-inch conduit for certain applications, such as high current feeders or large numbers of conductors. Using 3.5-inch conduit in such cases may not be compliant with code requirements. Fifthly, industry standard. 4-inch conduit has become the industry standard for larger electrical installations. Most electrical contractors and manufacturers are familiar with and prefer using 4-inch conduit for its reliability and ease of use. Therefore, it is generally recommended to upsize to 4-inch conduit instead of using 3.5-inch conduit. The increased availability, cost-effectiveness, ease of installation, code compliance, and industry standard make 4-inch conduit a more practical choice for most electrical projects. Conduit, in general, serves as a protective pathway for electrical wiring, safeguarding conductors from physical damage, moisture, and chemical exposure. The selection of appropriate conduit size is paramount for ensuring both safety and compliance with electrical codes. Factors influencing conduit size selection encompass the number and size of conductors, the fill ratio stipulated by the National Electrical Code, and the specific application at hand. Common conduit materials encompass rigid metal conduit, intermediate metal conduit, electrical metallic tubing, and rigid polyvinyl chloride conduit, each possessing distinct attributes suitable for diverse environments and applications. When embarking on electrical installations, meticulous adherence to local electrical codes and regulations is indispensable. Consulting with a qualified electrician or electrical inspector is advisable to ascertain that the chosen conduit size aligns with prevailing requirements and guarantees a secure and dependable electrical system. Electrical metallic tubing, commonly referred to as EMT, constitutes a prevalent conduit choice in electrical installations. Frequently termed thin-wall conduit, EMT stands out for its lightweight nature and ease of manipulation, rendering it well suited for an array of applications. EMT primary function lies in the protection of electrical wires and cables against impact, moisture, and chemical exposure. Typically crafted from steel or aluminum, EMT exhibits a galvanized or coated exterior to forestall corrosion. Its inherent flexibility streamlines bending and cutting, thereby expediting installation, particularly in confined spaces. EMT finds widespread application in both residential and commercial structures, commonly employed for branch circuits, lighting, and power distribution. Couplings and connectors serve the purpose of securely joining EMT sections and affixing them to electrical boxes or enclosures. The National Electrical Code dictates guidelines for EMT installation, encompassing support spacing, bending radii, and grounding requisites. EMT affordability, coupled with its ease of installation, renders it a favored selection for numerous electrical projects. Nevertheless, it's imperative to acknowledge that EMT is not appropriate for all applications. For example, in settings demanding heightened mechanical protection or resistance to corrosive substances, alternative conduit types such as rigid metal conduit or rigid polyvinyl chloride conduit may prove more fitting. When working with EMT, adherence to proper safety protocols is critical. Employing suitable cutting and bending tools, along with wearing personal protective equipment like gloves and safety glasses, is imperative to mitigate the risk of injury. Furthermore, ensuring correct grounding of EMT is essential to avert electrical hazards. In summation, electrical metallic tubing embodies a versatile and cost-effective conduit solution extensively employed in electrical installations. Its lightweight nature, ease of installation, and protective attributes render it a favored option among electricians and contractors. However, prudent consideration of the application's unique demands, alongside strict adherence to safety protocols and electrical codes, is indispensable when utilizing EMT. Rigid metal conduit, often abbreviated as RMC, represents a robust and unyielding conduit type employed in electrical installations demanding superior mechanical protection and structural fortitude. Commonly fashioned from steel or aluminum, RMC boasts substantial wall thickness, rendering it capable of withstanding significant impact and shielding electrical conductors from harm. RMC finds extensive application in outdoor environments, industrial settings, and locations prone to physical abuse. Its galvanized or coated exterior provides resistance against corrosion, thereby augmenting its longevity in harsh conditions. RMC installation necessitates specialized tools and techniques, encompassing threading, cutting, and bending. Threaded fittings and couplings are employed to securely join RMC sections and affix them to electrical enclosures. Due to its weight and rigidity, RMC installation may prove more arduous compared to alternative conduit types. The National Electrical Code delineates precise guidelines for RMC installation, encompassing support spacing, grounding prerequisites, and bending radii. RMC sturdiness renders it well suited for applications necessitating safeguarding against physical damage such as direct burial, exposure to corrosive substances, or encasement in concrete. It is frequently employed in industrial facilities, manufacturing plants, and outdoor infrastructure projects. While RMC offers exceptional protection, it tends to be more costly and labor-intensive to install compared to EMT or PVC conduit. Consequently, its utilization is typically reserved for scenarios where its unique attributes are indispensable. When working with RMC, adherence to proper safety protocols is paramount. Employing suitable threading, cutting, and bending tools, alongside donning personal protective equipment like gloves and safety glasses, is imperative to mitigate the risk of injury. Furthermore, ensuring correct grounding of RMC is essential to avert electrical hazards. In essence, rigid metal conduit constitutes a resilient and dependable conduit solution extensively employed in electrical installations necessitating superior mechanical protection and structural integrity. Its capacity to withstand impact, resist corrosion, and safeguard electrical conductors renders it an invaluable asset in demanding environments. However, prudent consideration of the application's specific demands, alongside strict adherence to safety protocols and electrical codes, is indispensable when utilizing RMC. Intermediate metal conduit, frequently abbreviated as IMC, constitutes a conduit type employed in electrical installations, striking a balance between the attributes of electrical metallic tubing and rigid metal conduit. Crafted from steel, IMC boasts a thinner wall thickness compared to RMC, rendering it lighter and more manageable to install. IMC serves the purpose of shielding electrical wires and cables against impact, moisture, and chemical exposure. Its galvanized or coated exterior provides resistance against corrosion, thereby augmenting its longevity in diverse environments. IMC installation necessitates specialized tools and techniques encompassing threading, cutting, and bending. Threaded fittings and couplings are employed to securely join IMC sections and affix them to electrical enclosures. While lighter than RMC, IMC offers superior mechanical protection compared to EMT, rendering it well suited for a broad spectrum of applications. The National Electrical Code delineates precise guidelines for IMC installation, encompassing support spacing, grounding prerequisites, and bending radii. IMC finds extensive application in both commercial and industrial settings, commonly employed for feeders, branch circuits, and control wiring. It is frequently utilized in locations demanding enhanced mechanical protection compared to EMT, but where the robust nature of RMC is not strictly necessary. IMC presents a cost-effective alternative to RMC, offering a compromise between protection and ease of installation. Its versatility and dependability render it a favored choice among electricians and contractors. When working with IMC, adherence to proper safety protocols is paramount. Employing suitable threading, cutting, and bending tools, alongside donning personal protective equipment like gloves and safety glasses, is imperative to mitigate the risk of injury. Furthermore, ensuring correct grounding of IMC is essential to avert electrical hazards. In summation, intermediate metal conduit embodies a versatile and dependable conduit solution extensively employed in electrical installations, necessitating a balance between mechanical protection and ease of installation. Its capacity to shield electrical conductors, coupled with its cost-effectiveness, renders it an invaluable asset in a wide array of applications. However, prudent consideration of the application's specific demands, alongside strict adherence to safety protocols and electrical codes, is indispensable when utilizing IMC. Rigid polyvinyl chloride conduit, often abbreviated as rigid polyvinyl chloride, constitutes a non-metallic conduit type employed in electrical installations, distinguished by its resistance to corrosion and its lightweight nature. Crafted from polyvinyl chloride plastic, rigid polyvinyl chloride conduit is impervious to rust and degradation caused by moisture, acids, and alkalis. Rigid polyvinyl chloride conduit finds extensive application in underground installations, direct burial applications, and settings prone to exposure to corrosive substances. Its smooth interior surface facilitates effortless wire pulling, streamlining the installation process. Rigid polyvinyl chloride conduit installation necessitates specialized techniques encompassing cutting, gluing, and the utilization of polyvinyl chloride fittings. Solvent cement is employed to securely join rigid polyvinyl chloride conduit sections and affix them to electrical enclosures. Rigid polyvinyl chloride conduit is non-conductive, thereby obviating the necessity for grounding. However, adherence to proper bonding techniques is crucial to ensure electrical safety. The National Electrical Code delineates precise guidelines for rigid polyvinyl chloride conduit installation, encompassing support spacing, burial depth, and expansion joint requisites. Rigid polyvinyl chloride conduit presents a cost-effective alternative to metal conduit in applications demanding corrosion resistance and lightweight construction. Its ease of installation and maintenance renders it a favored choice among electricians and contractors. However, rigid polyvinyl chloride conduit is more susceptible to physical damage compared to metal conduit, necessitating careful handling and protection. Furthermore, rigid polyvinyl chloride conduit may not be suitable for applications involving high temperatures or exposure to certain chemicals. When working with rigid polyvinyl chloride conduit, adherence to proper safety protocols is paramount. Employing suitable cutting and gluing tools, alongside donning personal protective equipment like gloves and safety glasses, is imperative to mitigate the risk of injury. In essence, rigid polyvinyl chloride conduit embodies a versatile and dependable conduit solution extensively employed in electrical installations necessitating corrosion resistance and lightweight construction. Its capacity to withstand harsh environments, coupled with its ease of installation, renders it an invaluable asset in a wide array of applications. However, prudent consideration of the application's specific demands, alongside strict adherence to safety protocols and electrical codes, is indispensable when utilizing rigid polyvinyl chloride conduit. Electrical boxes, often referred to as outlet boxes, junction boxes, or switch boxes, constitute integral components of electrical wiring systems, serving to enclose and safeguard electrical connections. These boxes are typically crafted from metal or plastic and are available in a multitude of shapes and sizes to accommodate diverse wiring configurations. Electrical boxes serve a multitude of purposes, encompassing the protection of wiring connections from physical damage, the prevention of accidental contact with energized conductors, and the provision of a secure mounting point for electrical devices such as switches, receptacles, and lighting fixtures. Metal electrical boxes are commonly fabricated from steel or aluminum and are frequently employed in locations demanding heightened mechanical protection. Plastic electrical boxes, conversely, are crafted from polyvinyl chloride or other non-metallic materials and are frequently utilized in damp or corrosive environments. Electrical boxes are equipped with knockouts, which are pre-cut openings that can be removed to facilitate the insertion of conduit or cable. These knockouts are meticulously sized to accommodate standard conduit and cable fittings, ensuring a secure and watertight connection. Installation of electrical boxes necessitates strict adherence to the National Electrical Code and local electrical codes. The National Electrical Code stipulates precise requirements for box fill, grounding, and mounting height, all of which are crucial for ensuring electrical safety. Box fill calculations determine the maximum number of conductors, devices, and fittings that can be safely accommodated within an electrical box. Overfilling an electrical box can lead to overheating, short circuits, and other hazardous conditions. Grounding is a critical safety measure that provides a low-resistance path for fault current to return to the source, thereby minimizing the risk of electric shock. Electrical boxes must be properly grounded to ensure that metallic parts are at the same potential as the earth. Mounting height requirements dictate the minimum and maximum height at which electrical boxes must be installed above the floor. These requirements are designed to ensure accessibility and prevent damage to electrical devices. When selecting electrical boxes, it is imperative to consider the specific application and the requirements of the National Electrical Code. Factors to consider encompass the size and type of conductors, the number of devices to be installed, and the environmental conditions. Proper installation of electrical boxes is paramount for ensuring the safety and reliability of electrical wiring systems. Consulting with a qualified electrician is advisable to ensure that electrical boxes are installed in accordance with all applicable codes and regulations. In summary, electrical boxes constitute essential components of electrical wiring systems, providing protection, safety, and a secure mounting point for electrical devices. Strict adherence to the National Electrical Code and local electrical codes is indispensable for ensuring the proper installation and operation of electrical boxes. Conduit fittings serve as essential components in electrical conduit systems, facilitating the connection and termination of conduit runs. These fittings are meticulously designed to ensure secure, reliable, and code-compliant installations. A diverse array of conduit fittings exists, each tailored to specific applications and conduit types. Common types of conduit fittings encompass couplings, connectors, elbows, tees, and bushings. Couplings are employed to join two sections of conduit, providing a continuous pathway for conductors. These fittings are available in both threaded and threadless designs, catering to different conduit types and installation requirements. Connectors are utilized to terminate conduit runs at electrical boxes, enclosures, or equipment. These fittings provide a secure and strain relief connection, safeguarding conductors from damage. Elbows are employed to change the direction of conduit runs, enabling routing around obstacles or within confined spaces. Elbows are available in various angles, including 90-degree and 45-degree configurations. Tees are utilized to create branch circuits or to split conduit runs into multiple directions. These fittings provide a convenient means of tapping into existing conduit systems. Bushings are employed to protect conductors from abrasion as they exit conduit runs. These fittings are typically installed at the end of conduit runs, providing a smooth and rounded surface for conductors to pass through. Conduit fittings are fabricated from a variety of materials, including steel, aluminum, and plastic. The selection of appropriate fitting material is contingent upon the conduit type, environmental conditions, and application requirements. Steel fittings are commonly employed with rigid metal conduit and intermediate metal conduit, providing exceptional mechanical strength and corrosion resistance. Aluminum fittings are frequently utilized with aluminum conduit, offering a lightweight and corrosion-resistant solution. Plastic fittings are typically employed with rigid polyvinyl chloride conduit, providing excellent corrosion resistance and electrical insulation. Installation of conduit fittings necessitates strict adherence to the National Electrical Code and local electrical codes. The National Electrical Code stipulates precise requirements for fitting selection, installation, and support. Proper installation of conduit fittings is paramount for ensuring the integrity and reliability of electrical conduit systems. Loose or improperly installed fittings can lead to electrical hazards such as short circuits, ground faults, and arcing. In summary, conduit fittings constitute essential components of electrical conduit systems, facilitating the connection and termination of conduit runs. Strict adherence to the National Electrical Code and local electrical codes is indispensable for ensuring the proper installation and operation of conduit fittings. Wire pulling lubricant plays a pivotal role in electrical installations, significantly reducing friction during the insertion of electrical conductors into conduit or other raceways. This lubricant, typically a polymer-based compound, streamlines the pulling process, minimizing the risk of damage to both the conductors and the conduit. The primary function of wire pulling lubricant is to diminish friction between the conductors and the interior surface of the conduit. By creating a slippery interface, the lubricant facilitates smoother and more efficient wire pulling, thereby reducing the force required to pull the conductors through the conduit. Wire pulling lubricant offers a multitude of benefits, encompassing reduced pulling tension, minimized conductor damage, enhanced wire pulling speed, and prevention of conduit damage. Reduced pulling tension alleviates strain on the conductors, diminishing the likelihood of insulation damage or conductor breakage. Minimized conductor damage safeguards the integrity of the conductors, ensuring optimal electrical performance and longevity. Enhanced wire pulling speed expedites the installation process, saving time and labor costs. Prevention of conduit damage protects the conduit from abrasion and wear, extending its lifespan and maintaining its structural integrity. A diverse array of wire pulling lubricants exists, each tailored to specific applications and conductor types. Common types of wire pulling lubricants encompass polymer-based lubricants, wax-based lubricants, and silicone-based lubricants. Polymer-based lubricants are the most prevalent type, offering excellent lubricity and compatibility with a wide range of conductor and conduit materials. Wax-based lubricants provide good lubricity and are particularly well suited for high-temperature applications. Silicone-based lubricants offer exceptional lubricity and are compatible with a wide range of conductor and conduit materials, including those sensitive to petroleum-based products. Application of wire pulling lubricant is a straightforward process, typically involving the application of a liberal amount of lubricant to the conductors as they are fed into the conduit. The lubricant can be applied manually, using a brush or rag, or mechanically, using a wire pulling lubricant applicator. When selecting wire pulling lubricant, it is imperative to consider the conductor type, conduit material, environmental conditions, and application requirements. Proper selection and application of wire pulling lubricant are paramount for ensuring efficient and damage-free wire pulling. In summary, wire pulling lubricant constitutes an indispensable tool in electrical installations, significantly reducing friction and facilitating smoother wire pulling. Proper selection and application of wire pulling lubricant are crucial for minimizing conductor damage, enhancing wire pulling speed, and preventing conduit damage. Electrical codes and standards serve as the bedrock of electrical safety, providing a comprehensive framework for the design, installation, and maintenance of electrical systems. These codes and standards are meticulously developed and rigorously enforced to safeguard individuals, property, and the environment from electrical hazards. The National Electrical Code, often abbreviated as the National Electrical Code, stands as the preeminent electrical code in the United States, offering a comprehensive set of guidelines for electrical installations. The National Electrical Code is meticulously updated every 3 years by the National Fire Protection Association, incorporating the latest technological advancements and safety practices. State and local jurisdictions frequently adopt the National Electrical Code, tailoring it to address specific local requirements. Electrical codes and standards encompass a wide spectrum of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. Wiring methods delineate the permissible techniques for installing electrical conductors, encompassing conduit, cable, and other wiring systems. Overcurrent protection mandates the use of circuit breakers and fuses to protect electrical circuits from overload and short circuits. Grounding establishes the procedures for connecting electrical systems to the earth, thereby minimizing the risk of electric shock. Equipment installation stipulates the requirements for installing electrical equipment, such as transformers, motors, and generators. Compliance with electrical codes and standards is not merely a matter of regulatory obligation but a fundamental aspect of responsible electrical practice. Adherence to these codes and standards ensures that electrical systems are designed, installed, and maintained in a safe and reliable manner. Electrical inspections serve as a critical component of the code compliance process, verifying that electrical installations adhere to the requirements of the National Electrical Code and local electrical codes. Electrical inspectors are qualified professionals who possess a thorough understanding of electrical codes and standards. Engaging a qualified electrician is paramount for ensuring that electrical work is performed in accordance with all applicable codes and regulations. Qualified electricians possess the requisite training, experience, and knowledge to design, install, and maintain electrical systems safely and effectively. In summary, electrical codes and standards constitute the cornerstone of electrical safety, providing a comprehensive framework for the design, installation, and maintenance of electrical systems. Compliance with these codes and standards is essential for safeguarding individuals, property, and the environment from electrical hazards.